What if I told you that the AI system that just generated a piece of art, or translated a language, or even beat a grandmaster at chess isn't just a clever piece of code? What if it's a reflection of something much deeper? A phenomenon governed by the same fundamental laws that forge stars, bind atoms, and dictate the very fabric of reality. We tend to think of artificial intelligence as a human invention, a product of silicon, logic, and brilliant engineering. But today, we're going on a journey to uncover a hidden truth. We're going to peel back the layers of algorithms and data and find, hiding in plain sight, the ghost in the machine, the laws of physics. This isn't a story about the ethics of AI, or even its latest applications. This is the secret origin story. It's a detective story spanning a century, connecting a simple model of a refrigerator magnet to the complexities of quantum mechanics. In a special collaboration with the brilliant minds at the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, or IAIFI, we're going to explore how computation, magnetism, and even the bizarre world of particle physics are not just related, but are facets of the same universal story. Prepare to have your understanding of both AI and the universe fundamentally changed. Let's begin by clearing the table. When we hear AI, our minds often jump to two places: either the practical tools changing our world, like Siri, ChatGPT, or self-driving cars, or the science fiction anxieties of super-intelligent machines. But both of these perspectives miss the most profound part of the story. They focus on what AI does, not what it is. The researchers at IAIFI aren't just building better AI. They're asking a more fundamental question. Why does it work at all? Why do these vast, complex networks of artificial neurons seem to possess an almost uncanny ability to learn, to recognize patterns, and to create? The answer, they're discovering, doesn't lie solely in computer science. It lies in the bedrock of reality itself, in physics. Imagine for a moment that our universe operates on a set of core principles. Principles of stability, of energy, of how systems of interacting parts find order amidst chaos. We see these principles everywhere. We see them in the way a snowflake crystallizes into a perfectly symmetrical shape, the way a galaxy spins itself into a spiral, and the way a living cell maintains its intricate structure. The stunning revelation is that these same principles are at play inside a neural network. The process of an AI learning to identify a cat in a photo is, at a deep mathematical level, analogous to a physical system settling into its most stable state. It's a process of finding equilibrium. This isn't just a handy metaphor, it's a deep structural correspondence. The math that describes how a collection of atoms becomes a magnet turns out to be shockingly similar to the math that describes how a network of neurons stores a memory. So, for the next little while, I want you to set aside the idea of AI as just software. Instead, think of it as a new kind of physical system we've learned to build. A computational clay that we can mold, but one whose properties are ultimately dictated by the timeless laws of nature. This is the story of how we stumbled upon that realization, and how it's now creating a powerful feedback loop, where physics helps us understand AI, and AI in turn helps us unlock the deepest secrets of the cosmos. Our story doesn't begin in a Silicon Valley garage. It begins a century ago, in 1920s Germany, in the mind of a physicist named Wilhelm Lenz. He was grappling with a question that seems simple, but is deceptively profound. Why is a magnet a magnet? Why does a block of iron, under the right conditions, suddenly gain the ability to attract or repel other objects? He knew it had to do with the atoms inside, but how? He gave this puzzle to his doctoral student, a young, brilliant man named Ernst Ising. Together, they developed a model of radical simplicity, one that would echo through science for the next 100 years. They imagined the iron not as a complex jumble of atoms, but as a simple grid, like a checkerboard. On each square of this board sat a single spin. You can think of a spin as a tiny, microscopic compass needle that can only point in one of two directions, up or down. Now here's where the physics comes in. These spins aren't isolated, they interact with their neighbors. They feel each other. Specifically, they prefer to align. An up spin wants its neighbors to be up, and a down spin wants its neighbors to be down. This alignment makes the system more stable. It lowers its overall energy, but there's a competing force: temperature. Temperature is a measure of random, chaotic energy. It's like a disruptive force shaking the checkerboard, trying to flip the spins randomly. So you have this beautiful cosmic battle playing out on a microscopic scale. On one side, you have the force of interaction, pulling the spins toward order and alignment. On the other, you have the force of temperature, pushing them toward chaos and randomness. When the temperature is high, chaos wins. The spins are a frantic, jumbled mess, pointing up and down randomly. The block of iron is not a magnet, but as you cool it down, as you remove that chaotic energy, the interaction force starts to dominate. The spins begin to whisper to their neighbors, "Hey, let's all point the same way." Suddenly, vast domains of aligned spins emerge, all pointing up or all pointing down. The block of iron snaps into a collective, ordered state. It becomes a magnet. Ising had created a model that, with just a few simple rules, explained a complex phase transition, the emergence of magnetism. He had shown how billions of tiny, local interactions could give rise to a single, large-scale, collective behavior. At the time, he might not have realized it, but he had just laid the first, crucial paving stone on the path to artificial intelligence. He had given us a language to talk about how simple parts, working together, can create a complex, stable whole. And that language was all about one thing: energy. To truly grasp the bridge between a magnet and a thinking machine, we need to introduce one of the most powerful and intuitive concepts in all of science: the energy landscape. Imagine a vast mountainous terrain. It's filled with soaring peaks, rolling hills, and deep, serene valleys. Now, place a marble anywhere on this landscape. What will it do? It will roll downhill. It will follow the path of least resistance, pulled by gravity, until it comes to rest at the lowest possible point it can find: a valley floor, a basin, a crater. It won't stop halfway up a hill. It won't balance precariously on a peak. It will seek out the lowest point. It will seek stability. This is a perfect metaphor for what happens in physical systems. Every possible configuration of a system, every possible arrangement of spins in the Ising model, for example, has an associated energy level. A random, chaotic arrangement of spins is like placing the marble on a high, precarious mountain peak. It's a high-energy, unstable state. An ordered, aligned configuration where all the spins point the same way is like the bottom of a deep, wide valley. It's a low-energy, highly stable state. Just like the marble rolling downhill, the system will naturally evolve over time to shed its excess energy and settle into one of these low-energy valleys. This is a fundamental drive of the universe. A hot cup of coffee cools down to match the room's temperature. A stretched rubber band snaps back to its shorter, more stable length. A chemical reaction proceeds in a direction that releases energy. All of these are examples of systems moving through their energy landscape, seeking a valley of stability. The Ising model's behavior can be perfectly described by this landscape. At high temperatures, the marble, the system state, has so much energy that it bounces all over the landscape, never settling down. But as the temperature drops, the marble loses its kinetic energy. It begins to feel the pull of the landscape's contours and inevitably rolls into one of the deep valleys, the up magnet state or the down magnet state. This visualization of a system navigating a landscape to find a stable resting point is the conceptual key that unlocks everything that comes next. It transforms a complex mathematical problem into an intuitive, physical journey. And it was this very idea that, decades later, would inspire a physicist to ask a revolutionary question. What if we could design the landscape? What if we could sculpt our own valleys, and in doing so, create not just a magnet, but a memory? Let's jump forward 60 years. The year is 1982. The world of physics has been transformed by quantum mechanics and relativity, and the digital revolution is just beginning. A physicist at Caltech named John Hopfield is thinking about two seemingly unrelated things: the spin glass models of magnetism that grew out of Ising's work, and the complex, mysterious network of neurons in the human brain. Hopfield saw a profound connection. He thought, what if a neuron is like one of Ising's spins? Instead of being up or down, a neuron can be on or off, firing or not firing. And what if the connections between neurons, the synapses, are like the magnetic interactions between the spins? Some connections could be excitatory, positive, encouraging the next neuron to fire. Others could be inhibitory, negative, discouraging it. And some could be neutral, having no effect. This was a brilliant leap of intuition. Hopfield realized he could build an artificial neural network based on the exact same principles as the Ising model. He created what we now call the Hopfield network. It's a collection of artificial neurons, each connected to every other neuron. The strength of these connections is defined by a set of numbers called weights, which could be positive, negative, or zero. And just like the Ising model, this network has an energy landscape. Any pattern of on and off neurons has a specific energy. The network, if left to its own devices, will naturally evolve toward a low energy state, a stable configuration, a valley in its energy landscape. But here is Hopfield's true genius. He figured out how to reverse engineer the process. Instead of just observing which valleys a system naturally has, he developed a rule, a learning rule, to create the valleys he wanted. He could take a pattern, say, the pattern of pixels that makes up a picture of a smiley face, and adjust the connection weights in such a way that this exact pattern became a low-energy valley in the system's landscape. He could essentially carve a memory into the fabric of the network. Here's how it works in practice. You show the network the smiley face and use a specific mathematical rule to set the weights between all the neurons. You've now sculpted the landscape. Now, you can show the network a corrupted or incomplete version of the image. A smiley face with one eye missing. This new pattern corresponds to placing our marble on the side of the smiley face valley. What does the network do? It follows the physics. The neurons begin to flip their states one by one, always moving in a direction that lowers the total energy of the system. The marble rolls downhill. And where does it stop? At the bottom of the valley, the perfectly restored original smiley face. The network had performed an act of associative memory. It had retrieved a complete memory from a partial cue. This was revolutionary. For the first time, we had a model that showed how a physical system, governed by principles of energy minimization, could store and retrieve information. The Hopfield network demonstrated that memory wasn't some abstract, ethereal concept. It was a physical state, a stable point in a high-dimensional landscape. The bridge between magnetism and the mind had been built. Hopfield's insight cracked open the door to modern machine learning. The key wasn't just that networks could have stable states, but that these states could be programmed. The process of learning, in this new paradigm, is the process of shaping the energy landscape. Think of a sculptor working with a block of marble. At first, the marble is formless. It has no specific shape, no deep valleys. The sculptor's job is to carefully chip away at the stone, to create grooves, contours, and depressions until a desired form, a statue, emerges. In the world of neural networks, the connection weights, or synapses, are the sculptor's chisel. And the learning algorithm is the technique the sculptor uses. Every time we train a modern AI, whether it's to recognize a voice, translate a sentence, or drive a car, we are engaging in this act of computational sculpture. We start with a network with billions of parameters, our digital block of marble, which are usually initialized randomly. The initial energy landscape is mostly flat and featureless. Then we show it data. Lots and lots of data. We show it thousands of pictures of cats, and for each one, we tell it, this is a cat. If the network gets it wrong, the learning algorithm kicks in. It makes tiny, precise adjustments to millions of those synaptic weights. Each adjustment is like a tiny tap of the chisel. It slightly lowers the energy of the landscape for cat-like patterns of input and raises it for others. We repeat this process millions, even billions of times. With each example, The chisel taps again, deepening the cat valley. Over time, a vast and incredibly complex landscape is formed. It has a deep valley for cat, another for dog, another for car, and so on for every category it has learned to recognize. When you finally show the trained AI a new picture of a cat it's never seen before, that input pattern places the marble somewhere on this vast landscape. And because of the millions of tiny adjustments made during training, it almost inevitably finds itself on the slope of the cat valley. The network's state rolls downhill, converges to that stable point, and the output is cat. This fundamental principle, learning by adjusting connection strength to shape an energy landscape, is the beating heart of almost all modern AI. It scaled from Hopfield's small networks to today's behemoths like GPT-4, which have hundreds of billions or even trillions of parameters. The scale is different, but the core physical idea is the same. We are not programming intelligence with explicit rules. We are creating a physical system with the right kind of landscape and letting the laws of energy minimization do the rest. We are landscape artists, and our medium is computation. For a long time, the analogy of neurons and synapses was incredibly useful. It connected AI back to biology and gave us an intuitive way to think about these systems. But to go deeper, to find the connection to fundamental physics, scientists had to take a step back and look at the system through a different lens, the lens of pure mathematics. Let's move away from the brain analogy for a moment. What is a neural network, really? At its core, it's a giant mathematical function. It's a machine that takes a set of numbers as input, like the pixel values of an image, and through a series of calculations defined by its parameters, produces a set of numbers as output, like the probability that the image is a cat. It's a mapping from an input space to an output space. Now, let's think about what a field is in physics. A field is a physical quantity that has a value for every point in space and time. A temperature field, for example, assigns a temperature value to every location in a room. A gravitational field assigns a specific force vector to every point in the cosmos. It's a map of values spread across a space. A neural network can be viewed in exactly the same way. It defines a field over the space of all possible inputs. For every possible input image, the network assigns an output value. Changing the network's parameters, the weights and biases, is like turning a set of cosmic knobs that change the shape and behavior of this entire field. You're not just changing the output for one input, you're warping the entire landscape of possibilities. This shift in perspective is crucial. It moves us from thinking about individual, discrete components, neurons, to thinking about a continuous, holistic entity, the field. It's like shifting from looking at individual water molecules to looking at the currents and waves of the ocean. Once you see a neural network as a field, you can start to ask the same kinds of questions physicists ask about their fields. How does this field behave on average? How do its values fluctuate from point to point? Is there a statistical pattern to its behavior? This mathematical reframing was the key that allowed researchers to discover a law hidden within the apparent chaos of these massive networks, a law that would connect them directly to the statistical heart of physics. In 1995, a brilliant researcher named Radford Neal made a discovery that would prove to be foundational. He was exploring a question that seems simple on the surface. What happens to a neural network when you make it really, really wide? That is, what if you keep adding more and more neurons to its hidden layers, taking it towards an infinite width? You might expect the network's behavior to become infinitely complex, a chaotic mess of calculations. But Neal found the exact opposite. As the network grew wider, its behavior actually became simpler and more predictable. Specifically, the distribution of its outputs for any given input converged to a perfect and familiar shape. The Gaussian distribution, better known as the bell curve. This is a stunning example of emergent simplicity. The bell curve is nature's signature of randomness and aggregation. Think about it. If you flip a single coin, the outcome is random, heads or tails. But if you flip 10,000 coins and count the heads, the results of repeating this experiment will form a perfect bell curve. The heights of a large population of people, the measurement errors in a scientific experiment. So many complex systems, when viewed statistically, average out into this elegant shape. Radford-Neal showed that an infinitely wide neural network behaves as a Gaussian process. This means that even though the network itself is a complex, deterministic function, its statistical behavior is beautifully simple and governed by this universal law. The contributions of all the individual neurons, each with their random initial weights, average out in just the right way to produce this smooth, predictable Gaussian output. This was a monumental discovery. It was like finding a law of nature within an artificial, man-made system. It suggested that there are fundamental mathematical principles governing AI that don't depend on the specific architecture or the training data. It established that, in a specific mathematical limit, AI wasn't just a jumble of ad hoc engineering tricks. It was a system with its own thermodynamics, its own predictable statistical laws. This Gaussian connection was more than just a mathematical curiosity. It provided a new, powerful theoretical tool to understand AI. But more importantly, it was a piece of a puzzle that, decades later, would be slotted into place next to another, even more profound area of physics, the quantum world. And this brings us to the bleeding edge of research, to a jaw-dropping discovery made in 2020 by the very researchers at IAIFI we're collaborating with today. They took Neal's Gaussian process discovery and looked at it through the lens of their own field, quantum field theory. And what they found was a parallel so deep it sends shivers down the spine. Quantum field theory, or QFT, is the language we use to describe the fundamental particles and forces of the universe. In QFT, the most basic components of reality are not tiny solid particles, but rather omnipresent vibrating fields. There is an electron field, a photon field, and so on, filling all of space. What we perceive as a particle, like an electron, is just a localized energetic vibration, a quantum fluctuation, in its corresponding field. Now, consider the simplest kind of quantum field, a free field, one that isn't interacting with any other fields. If you were to measure the value of this field at any point in space, you wouldn't get a fixed number. You'd get a random value drawn from, you guessed it, a Gaussian distribution. The fundamental, baseline behavior of a non-interacting quantum field is to fluctuate randomly according to a perfect bell curve. The connection is breathtaking. An infinitely wide neural network is a Gaussian process. A free quantum field is also a Gaussian process. Mathematically, at this deep statistical level, they are the same kind of object. The random outputs of an untrained, infinitely wide AI mirror the random quantum fluctuations of an empty universe. But the analogy gets even better. Of course, our universe isn't made of free, non-interacting fields. Fields interact. An electron field interacts with a photon field, and this interaction is what gives rise to the force of electromagnetism and all the complexity we see around us. When fields interact, their behavior is no longer perfectly Gaussian. Physicists have spent decades developing complex mathematical tools, like Feynman diagrams, to calculate the corrections needed to describe these interactions. And here is the final, stunning piece of the puzzle. The IAIFI researchers found that a finite-width neural network, a real-world network that doesn't have an infinite number of neurons, behaves exactly like an interacting quantum field. The deviation from the perfect Gaussian behavior that you get by having a finite number of neurons is mathematically analogous to the corrections physicists calculate for interacting quantum particles. Two vast realms of science, born a century apart and from completely different motivations. One to describe the microscopic dance of subatomic particles, the other to create intelligent machines, turned out to be speaking the same deep mathematical language. It suggests that the principles governing how information is processed in these complex networks are not arbitrary, but are tied to the most fundamental ways our universe is structured. This profound theoretical bridge isn't just an academic curiosity. It is already opening up revolutionary new frontiers in scientific research. It's creating a powerful two-way street where AI and physics supercharge one another. For decades, physicists have struggled to simulate certain aspects of the universe. While supercomputers are incredibly powerful, some problems, particularly those involving the strong nuclear force that binds quarks together inside protons and neutrons, are just too complex. The number of possible interactions in these quantum systems explodes exponentially, quickly overwhelming even the world's fastest machines. But now, with this newfound connection, a new approach is possible. If a neural network naturally behaves like a quantum field, then perhaps we can use a neural network as a quantum field simulator. Instead of trying to brute force the calculations on a supercomputer, we can set up a neural network with the right structure and let it find the low-energy, stable states of the system on its own. It's like using a system that already speaks the language of quantum statistics to solve problems in that language. It's a more natural and potentially vastly more efficient way to model the universe. Physicists are now exploring using these techniques to simulate the behavior of quarks and gluons, to understand the dynamics of complex quantum symmetry models, and to probe the mysteries of the early universe. This fusion of AI and quantum physics isn't just an incremental improvement. It hints at a paradigm shift in how we do theoretical physics. We may soon be able to explore corners of the quantum world that were previously completely inaccessible. Imagine being able to simulate the core of a neutron star, or the moments after the Big Bang, not with equations on a blackboard, but by training a neural network. This is the promise of this deep connection, turning AI from a mere data analysis tool into a new kind of theoretical laboratory for exploring the fundamental nature of reality. So, we've come full circle. Our journey began with a simple physical model of a magnet and ended in the esoteric world of quantum field theory. Along the way, we discovered that the inner workings of AI are not a black box of arbitrary code, but a physical phenomenon reflecting the universe's deepest laws. This is a story of a beautiful symbiosis. AI is now a critical tool for physics. It's being used to filter out noise from the faint signals of gravitational waves, giving us a clearer view of colliding black holes. It's sifting through the petabytes of data from particle accelerators like the Large Hadron Collider, helping to find the faint signatures of new particles. AI is simulating new materials with exotic properties and mapping the invisible scaffolding of dark matter that holds our galaxies together. But at the same time, physics is giving back to AI. The concepts of energy landscapes, statistical mechanics, and now even quantum field theory are providing a solid theoretical foundation for why AI works. This understanding helps us build better, more efficient, and more reliable AI systems. It turns the art of AI engineering into a science, grounded in first principles. The union of these two disciplines elevates artificial intelligence from a computational tool into a genuine physical phenomenon, one that learns and processes information according to the same principles of stability and interaction that govern everything from a magnet to a galaxy. So, what's the lesson for us in our daily lives? This grand story about the cosmos and computers has a surprisingly personal application. Think about your own mind. Your brain, too, is a network, and your habits and thought patterns create their own kind of energy landscape. A bad habit, like endlessly scrolling on your phone, is a deep, well-worn valley in your neural landscape. Your brain rolls into it easily, seeking that low-energy state of comfort and distraction. Learning a new skill or building a good habit is the hard work of sculpting a new valley. It takes repetition and conscious effort, the mental equivalent of chipping away at marble. At first, the new valley is shallow, and it's easy for your marble to roll back into the old, deeper one. But with persistence, you deepen the new path until it becomes the new default, the new state of stability. The advice, then, is to be a conscious sculptor of your own mental landscape. Recognize the valleys you inhabit. Actively work to create the ones you want. Understand that building a better life, much like training an AI, is a physical process of carving new, healthier, and more productive pathways for your energy to flow. It leaves us with some incredible questions to ponder. What other hidden laws of nature are being expressed in the complex systems we build? If the rules of quantum fields are mirrored in AI, what does that imply about the nature of information and computation in our universe? I'd love to hear your thoughts on this in the comments below. Which part of this century-long story surprised you the most? Thank you for joining me on this incredible journey through physics, memory, and the mind of the machine. I hope it's given you a new appreciation for the deep and beautiful order that underlies our world. Please take care of yourselves and stay curious. And if you enjoyed this exploration and want to dive deeper into the biggest ideas in science, please consider liking this video and subscribing to the channel. It helps us continue to bring these stories to you. Until next time.